Hi everybody, and welcome to another Intro to Advanced Math lecture. I'm going to be doing some exercises by induction today, and what's special about these exercises is that they have absolutely nothing to do with sums and summations. All of the exercises that we've done up to this point have involved sums, summations, and so forth. The exercises that I'm going to do today are not going to involve sums of real numbers, summation signs, anything like that. The proposition that we're going to prove is that the polynomial x to the n minus 1 has a factor of x minus 1 for all natural numbers n. So what's our first step? By the way, I did mention the word proposition, didn't I? So maybe I should note this is our proposition, P of n. Our first step is to show that our proposition is true for n equal 1. Our first step, show that the proposition is true for n equal 1. Now I claim that when n equals 1, x to the n minus 1 is just x minus 1. And this expression has x minus 1 as a factor. We can write x minus 1 times 1. And I'm going to write it like this because I need, and I should have done this earlier, I need to define exactly what I mean when I say this polynomial x to the n minus 1 has x minus 1 as a factor. I've showed this for n equal 1. And I'm going to explain how it is that I've shown that x to the first minus 1 has x minus 1 to a factor, as a factor, according to the criterion that we're going to use to define this as having a factor. By the way, what that means is, I should have told you this earlier, but I'm telling you now. X minus 1 has x to the n minus 1 has x minus 1 as a factor. Exactly when x to the n minus 1 can be expressed in this way. X to the n minus 1 equals p of x times x minus 1, where p of x is a polynomial in the variable x. So x to the n minus 1 has x minus 1 as a factor. Exactly when we can write x to the n minus 1 as the product of x minus 1 times some polynomial. Did we do that in the case of n equal 1? n equals 1, we have x to the 1 minus 1, which is just x minus 1. And oddly enough, I didn't stop here. I wrote it as x minus 1 times 1. And if you're thinking, is this our p of x in this case? The answer is yes. Really? Well, where's the x? Think back on the definition of a polynomial. A polynomial is just the sum of monomials. And what's a monomial? A monomial is the expression c times x to the n, where c is any real number and n is a non-negative whole number. One equals the real number 1 times x to the power of this non-negative whole number, 0. So this is our polynomial p of x. And in the process of defining monomial this way, have I just admitted that every real number is a monomial? Yes, I have. And since a polynomial is the sum of one or more monomials, every monomial is a polynomial. Here's a monomial. It's also a polynomial. So I expressed x to the power of 1 minus 1 as x minus 1 times some polynomial. X minus 1 is a factor of x to the first minus 1. And down here, I'll just confirm P of n is true for n equal 1. That's our first step. Our next step, assume that our proposition is true for some natural number k. That's our induction hypothesis. And show that our proposition is true for k plus 1. Second step, assume our proposition is true for a natural number k, that's our induction hypothesis, and show that the proposition is true for n equal k plus 1. In terms of our specific exercise, that means we want to show that x to the k minus 1 has a factor of x minus 1. That's our induction hypothesis. And we want to show that x to the power of k plus 1 minus 1 also has a factor of x minus 1. Okay, so here we start with x to the k plus 1 minus 1. I have to show that this has a factor of x minus 1. And I don't know anything about x to the k plus 1. I do know something about x to the k. I know by my induction hypothesis that x to the k minus 1 is equal to x minus 1 times some polynomial in x. That's my induction hypothesis, that x to the k minus 1 has x minus 1 as a factor. It's equal to x minus 1 times some polynomial in terms of x. So I want to take this k plus 1, or x to the k plus 1 that I know nothing about, and write it in terms of x to the k. Now that's not really all that significant, but at least I have something in terms of x to the k here. You know what would be really nice is if somehow I could have x minus 1 here instead of just x. But we'll settle for small victories at first. I have x times x to the k minus 1. And here's what I think I'll do. Well, I can't do that. In essence, I've subtracted x from this expression. Well, let's see. I have x to the k plus 1, or x times x to the k, I have that, minus x, oops, I don't have an x in here that I'm subtracting, but I've subtracted x. I have to atone for my sin by adding x back. Does that get me where I want to go? Let's see. I have x times x to the k minus x plus x. Oop, the only thing I'm missing, I don't have a negative 1 out here. So I'm going to put that right here. And let me look at it again and make sure that what I've done is mathematically sound. Now, I will say this. I don't know for sure that this is going to work. It may not. I'm just going with my intuition. And if it doesn't work, it doesn't mean that I had a bad idea. It just means that I had a good idea that didn't work. And the same with you when you do a proof. If you choose a direction to go in and you end up painted in a corner and you can't get out, it doesn't mean you had a bad idea. It means you had a good idea that just didn't pan out. Now let's see if what I've done is mathematically sound. X times x to the k, I got that. And then I have minus 1, that's this thing. And let's see, I have minus x and plus x is 0. Yeah. So everything's fine. You know what? Now I have things written in terms of x to the k minus 1. I can use my induction hypothesis. And what is my induction hypothesis? That this thing equals x minus 1 times some polynomial p of x. And this thing, that's just x minus 1. By our induction hypothesis, this thing has a factor of x minus 1. It's equal to x minus 1 times some polynomial p of x. And oh, isn't this nice? This term has a factor of x minus 1. And this term has a factor of x minus 1. I can factor out x minus 1. I factor x minus 1 out of this, and I have x times p of x. I factor x minus 1 out of this term, and I have 1. Is x times a polynomial a polynomial? It is. X times a polynomial is a polynomial that is of degree 1 greater than the polynomial itself. So this thing is a polynomial. If I add 1 to a polynomial, do I get a polynomial? Yeah. A polynomial is the sum of one or more monomials. This is a monomial. I'm adding it to a polynomial. I get another polynomial. And I'm going to call this polynomial q of x. Now let me conclude. I've actually shown everything that I've had to show. Now we tie up everything nicely. We assumed the proposition was true for n equal k, and we used that to show that the proposition is true for n equal k plus 1. So we conclude our proposition is true for all natural numbers n. That is, x to the n minus 1 has x minus 1 as a factor for all natural numbers x.